Hi, this is Soikat Majumdar. Today we will discuss the second part of the statistical mechanics. Here we will cover the topics ensembles, phase space, density of states. Learning objective is to compute macroscopic properties from the quantum mechanical information about the atoms and molecules of interest. First, let us start with ensembles. As a system is defined by the collection of large number of particles. So, the ensembles can be defined as a collection of a number of macroscopically identical but essentially independent systems. Here, the term macroscopically independent means as each of the systems constituting an ensemble satisfied same macroscopic conditions like volume, each of the systems having same volume, same energy, same pressure, same temperature and same total number of particles. That means each of the systems will maintain same V, same energy, same pressure, same temperature and total number of particles N, etc. Here again the term essentially independent means the system in the ensemble being mutually non-interacting to others. That is, the system differing macroscopic conditions like parity, symmetry, quantum states, etc. That means ensemble as a whole, the assembly of systems. In general, the collection of very large number of identical, non-interacting macroscopic systems is called ensembles. There are three types of ensembles. One, microcanonical ensemble. Two, canonical ensemble. Three, grand canonical ensemble. Suppose we have taken here 16 systems. Each system having system 1, 2, 3, 4 up to system 16. Each system having same pressure, same number of particles, same temperature, same volume, same energy. So these are macroscopically identical. Basic conditions are macroscopically identical and independent systems. So it is collection of large number of systems. Here we have diagrammatically represented the ensembles. It is as a whole is known as an ensemble. Total systems as a whole is known as an ensemble. Assembly of systems. Microcanonical ensemble. It is a system or it is a collection of a large number of essentially independent systems having same energy, volume and total number of particles N. That means all the systems having same energy, same volume and same number of particles. The system of a microcanonical ensemble are separated by rigid, impermeable, separated by rigid, impermeable and insulated walls such that the values E, V, N are not affected by mutual pressure of the system. That means these walls are the borders. The walls are rigid, impermeable. So no system can interact with the other. Then energy, volume and number of particles are not affected by the mutual pressure of the system. Microcanonical ensemble cannot exchange neither energy nor matter with each other. There is no exchange of energy nor the matter. There is no change in E and N. Canonical ensemble. It is a collection of a large number of essentially independent systems having the same temperature T, volume V and the number of particles N. Here we have taken a system, assembly of systems where T, V and N are fixed. All the systems having same T, V and N. Now we have removed the borders here. Why? Here also the walls are rigid and impermeable, but they are conducting. In canonical and in microcanonical ensembles, the walls are rigid and impermeable, but they are not conducting. Here the walls are conducting. So the equality of temperature of all the systems can be achieved by bringing all the systems in thermal contact. Hence, in this ensemble, the systems are separated by rigid, impermeable but conducting walls. The outer walls of the ensemble are perfectly insulated and impermeable through. If the physical system exchange energy but not matter with each other, the corresponding ensemble is called canonical ensemble. Now grand canonical ensemble. If the collection of large number of essentially independent systems having the same temperature T, volume V and chemical potential mu, then the ensemble is known as the grand canonical ensemble. Here we have represented the assembly having same temperature, same volume and same chemical potential. The systems of grand canonical ensemble are separated by rigid, permeable, not impermeable. Here it is permeable and conducting walls. If the physical system exchange both energy and matter with each other, the corresponding ensemble is called grand canonical ensemble. It will transfer. Why? The energy and matter, basically the walls are rigid, permeable and conducting. That's why they will exchange both energy and matter. So this is the grand canonical ensemble. So in a nutshell, these are all the types of ensembles. Thermodynamic probability. The total number of possible microstates of a system corresponding to a given macrostate is called thermodynamic probability, or total number of microstates in a given macrostate is called thermodynamic probability. For n particles, the number of microstates for its n1, n minus 1 macrostate is, you can represent it n1, n minus 1 is equal to n factorial by n1 factorial, n minus n1 factorial. So we have taken an example. There are 4 distinguishable particles. That means particles are represented by A, B, C, D. Distinguishable, that we can distinguish them. For its 1, 3 macrostate, this is 1, this is 3. The number of microstates will be W, 1, 3 will be number of particles 4 factorial. First, this one is 1 factorial 1 and this one is 3 factorial 3. So it is 4. So total number of thermodynamic probability will be 4. Or total number of microstates in the given macrostate will be 4. Now come to the thermodynamic probability and entropy. Entropy of an isolated system always increases when the system undergoes an irreversible process. So, ice to water then vapor, again vapor to water then ice, it is a reversible process. But say we are pumping some body, suppose we are using some mechanical device, we are pumping it, then what will happen? Energy is produced, it will go outside. If we remove the energy, we cannot come back to the previous position. This is an irreversible process. When the system reaches an equilibrium, the entropy becomes maximum. In equilibrium, all the microstates of a system are equally probable. Hence, all the microstates, that is the arrangement W of atoms in the energy states of the system, should also come to a maximum value. Let sigma be the entropy of the system. So there must be a correlation between sigma and W. Sigma is the entropy, W is the thermodynamic probability, that is the number of microstate in a given macrostate. To correlate sigma and W, we consider two identical systems A and B in thermal contact with each other. That means A and B are in thermal contact with each other. Let the entropy of the systems A and B be sigma A and sigma B, and the thermodynamic probabilities be WA and WB respectively. The total entropy of the composite systems sigma is equal to sigma A plus sigma B. Thus we can write sigma is equal to function of W. If we think sigma is functionally related to W, this is, we have written sigma is equal to FW. Sigma is functionally related to W. This is sigma is equal to FW. So we can write FW, this is a composite system, is equal to FWA plus FWB. This is possible only if the functional form is in logarithmic form, that is sigma is equal to K log W. Here K is the Boltzmann constant, its value is 1.38 10 to the power minus 23 joule per Kelvin. Phase space. This is a new term, phase space. It is very important in statistical mechanics. With the phase space, we have to do everything. To describe both the position and the state of motion of the particle, it is required to set up a 6-dimensional space in which a point has 6 coordinates, 3 position coordinates x, y, z and 3 momentum coordinates px, py and pz along 6 mutually perpendicular axes in space. A point in this space describes both the position and momentum of the particle at some particular instant. This combined position and momentum space for a single particle is called phase space. So it is a 6-dimensional space. It contains 3 position coordinates and 3 momentum coordinates, and they are mutually perpendicular in space. Phase space of simple harmonic oscillator. For a one-dimensional simple harmonic oscillator of mass m and spring constant k, the total energy at any instant for its displacement x from its equilibrium position can be written as total energy E is equal to kinetic energy plus potential energy. So E is equal to half m x dot square. X dot means velocity, so v square, half mv square plus half kx square. So now mx dot square means m square x square by 2m. That means this one is px square by 2m. We have written here px square by 2m plus half kx square. As the momentum of the harmonic oscillator is px is equal to mx dot. So if we divide both sides by E, then it becomes x square by 2e by k plus px square by 2m. This is the equation of ellipse. So the phase space of two-dimensional and xpx plane forms a curve. This is known as the phase trajectory. Here the phase trajectory of a simple harmonic oscillator is an ellipse with semi-major axis is root over 2e by k and semi-minor axis is root over 2m. So phase trajectory of a simple harmonic oscillator is an ellipse. Now density of states. Density of states means number of quantum states or unit cells within the energy range E and E plus D in the phase space, or number of states per unit volume. Let us calculate. This is for a single particle of mass m and volume v. The elementary phase volume for a single particle can be written as dqx, dqy, dqz, and corresponding momentum dpx, dpy, dpz. Now from Heisenberg uncertainty we know that uncertainty in position delta x delta px is equal to h cut. So we are writing here h cut is small, so h. So delta, so dx dpx or dqx dpx we can write it as h. So this dqx dpx h, this dqy dpy is h, this dqz dpz is also h. So we are writing here as hq. So which is the volume of the phase cell or phase point in phase space. So the total volume of the phase space is, we are taking the volume integral. For this 3 we are taking 3 integrals, and for this 3 we are taking 3 integrals. But dqx, dqy, dqz, its volume integral is equal to volume integral is dx, dy, dz, and we can write it as capital V of the particle. So total volume of the particle V is equal to volume integral dx, dy, and dz. Thus the volume becomes V, again volume integral dpx, dpy, dpz. Now the volume of the momentum space containing momentum p and p plus dp is given by the volume of a spherical shell of radius p and thickness dp. Therefore volume integral dpx, dpy, dpz can be written as its surface integral is surface area is 4 pi p square and thickness is dp. So 4 pi p square dp, it becomes the volume of this spherical shell having width dp. Thus the volume of phase space becomes, this one is v and this one becomes 4 pi p square dp. But the volume of phase cell is hq. Volume of a unit cell, that is, a unit cell is hq. So number of phase space or number of cells will be this total volume by the volume of a unit cell. Then we will find out the number of unit cells. Therefore, the total number of phase cells in the momentum range P to P plus dp is GPdp. We are representing it as GPdp is equal to total volume by volume of a unit cell. So we are getting number of phase cells. This is the total number of phase cells. Total volume by volume of unit cell. If the energy corresponding to momentum P is capital E, so E is equal to P square by 2m or P is equal to root over 2me. If we differentiate, dp becomes root over 2m, m by, that means root over m by 2e into de. Thus, the total number of microstates in the energy range from E and E plus de is GED plus 1 by h cube v 4 pi, p square means 2me and dp means root over m by 2e de. So it becomes 1 by h cube 4 pi v root over 2 e m to the power 3 by 2 de. So therefore total number of microstates per unit energy range is 1 by h cube 4 pi v root over 2e m to the power 3 by 2. For the particles having two allowed values of spin quantum number, ms is equal to plus minus half. The number of available quantum states, that is the cells, is 2 times of that given by the equations. Thus, total number of phase cells in the momentum range P and P plus dp is GPdp, and initially it is multiplied by these two states, 2 into, already we have calculated GPdp means this v into 4 pi p square dp by h cube, putting here, so it becomes 8 pi v p square by h cube dp. The total number of quantum states in the phase space within the energy range E and E plus d is, already we know GED is this 1 by h cube 4 pi v root over 2e m to the power 3 by 2 d, putting here 2 into this 4 pi means 8 root 2 pi v by h cube m to the power 3 by 2 e to the power half, that was e to the root over e. Now here we are writing here e to the power half d. So total number of quantum states in the phase space within the energy range E and E plus d becomes 8 root 2 pi v by h cube m to the power 3 by 2 e to the power half de.